Ladies and gentlemen, in analyzing the coffee roasting process, we often speak of the first crack merely as a temporal marker, a familiar pop. But today I ask you to look beyond the sound for a moment and consider the event occurring at the microstructural level. It is a remarkably complex phenomenon existing at the intersection of materials science and thermodynamics. 1. The initial condition, the glassy fortress. In its raw or green state, the coffee bean is essentially an amorphous solid existing in a glassy state. This means its molecular structure is rigid, disordered, and locked in place as it exists at a temperature below its glass transition temperature. Its complex polysaccharide matrix, primarily composed of galactomannans and arabinogalactans, acts as a formidable fortress. Its cellular structure is, for all practical purposes, impermeable. 2. Pressurization, the miniature reactor. As we input thermal energy, the initial phase is endothermic. This energy is consumed to vaporize the free moisture, which constitutes roughly 10 to 12% of the bean's mass. At this point, a critical imbalance begins to build from within. Source 1, steam H2O. The water trapped within the cellular structure, unable to escape, boils and becomes high-pressure vapor. Source 2, gases, pyrolytic reactions and complex chemical pathways such as Strecker degradation begin to liberate significant volumes of gases, primarily carbon dioxide, CO2. The fundamental problem is this: the rate of gas production is exponentially faster, by orders of magnitude, than the rate of diffusion out of the still rigid, glassy structure. The gas and steam are thus trapped. This generates immense internal pressure. We are not speaking of trivial forces. We are speaking of internal pressures reaching 16 to 18 bars, with models suggesting peaks as high as 25 bars. Every single bean in that roaster has become a miniature pressurized reactor, balanced on the knife edge of failure. 3. The tipping point, crossing the glass transition temperature. And then we reach the most critical inflection point. As the internal core temperature of the bean continues to rise, it finally crosses its glass transition temperature. The bean's entire physical world changes in an instant. The polymer structure, once rigid and brittle as glass, suddenly gains molecular mobility. It transitions quite rapidly from the glassy state to the rubbery state. Its viscoelastic properties are fundamentally altered. The cell walls, which were the strong containment vessels, are now soft, pliable, elastic, and crucially, weak. 4. The fracture, a catastrophic mechanical failure. At this precise moment, the equation is no longer balanced. You have softened, pliant, rubbery cell walls, attempting to contain a supercritical internal pressure of 18 bars. The structure cannot hold. What happens next is not a chemical event. It is a catastrophic mechanical failure. We observe a rapid explosive fracture of the cellular matrix. The structural integrity fails. The crack we hear is simply the acoustic signature of this failure, the sound of high-pressure gases and steam violently escaping their prison, forcing the bean structure to expand and rupture. This event is not merely destructive, it is creative. It fundamentally re-architects the bean. The once dense, impermeable solid is transformed into a highly porous, sponge-like structure. This new architecture, this porosity, is the very thing that permits the final crucial stage of coffee's purpose, extraction. Without this violent mechanical fracture, the hot water of brewing would find no purchase, no pathway to the complex oils and soluble compounds we seek. Pause. That is the physics behind the pop. Thank you.